All right. The next talk will be by Yuanfeng on abstraction refinements for a Bayesian program analysis from Peking University.
Okay, thank you. Hello, everyone. I'm Yuanfeng from Peking University. I'm going to talk about our recent work on abstraction refinement for Bayesian program analysis. This is a joint work with Yifan, Zhang, and Zhang. We begin with an introduction to Bayesian program analysis, which is a new paradigm to address problems existing in conventional program analysis. An analyzer will generate alarms based on logic rules and provide them to the user. However, there are many false positives due to the approximation. The analyzer also cannot learn and adapt to the user's needs because the logic rules are fixed. To address these problems, Bayesian analysis converts conventional ones into Bayesian models. As a result, it can learn from posterior information such as user feedback, order version code, and test runs. It can also generate the probabilities of alarms to rank them. Therefore, compared to conventional analysis, it can significantly improve users' experience. Next, let's focus on the key component of program analysis, abstraction selection. For conventional one, there is a trade-off between precision and scalability here. Moreover, for Bayesian one, abstraction also heavily affects its generalization ability, which means its ability to learn from posterior information. So, how to select proper abstractions to achieve a balance between precision, scalability, and generalization becomes a challenge. To address this issue, our group proposed an offline learning-based approach, but it may work not so well, especially when the new program is out of the distribution of the training set. And inspired by the cigar technique, in this paper we propose an online approach, and I will use an example to explain it. Here is the example program. Method input 1 always generates odd numbers, while input 2 always generates even numbers. A data flow analysis is applied to resolve potential division by zero alarms. Here the divisors in x1, x3, and x5 cannot be zero as they are all odd. But for x2, x4, it is possible as they are even. And we additionally assume the analysis doesn't know the specifications of input functions. Hence, those functions can produce any integer, and this numeric analysis will degrade to a tent analysis. Then we can cast it as a graph reachability problem as shown by this figure. And we should conservatively assume data flow from both input 1 and input 2 are tented. Then the directed edges denote data flows in the program, and the analysis will report alarms for x1 to x5 as the tented data flow from I1 and I2 will reach them. However, as you can see, such approximation introduces false alarms here, x1, x3, and x5. So in Bayesian analysis, we can attach a probability 0.99 to each variation to quantify their degrees of approximation. Note that such probability can use machine learning tools to assign. Here we just use 0.99 for our illustration. For example, if tent I2 is true, then the probability of tent Y being true will be 0.99. After that, the whole graph is transformed into a Bayesian network, and each tuple becomes a random variable. We can do Bayesian inference on each variable based on given posterior information like user's feedback. For example, we can first calculate the probability of A1 to 5. Here, alarm xi is simplified as AI. For A1, A3, A5, we all have the same highest probability. Therefore, the user checks A1 and gives negative feedback. Then, based on that, we can calculate the conditional probability under this feedback. The probabilities of A2 to A5 all decrease, since the negative feedback will blame them common father node, tent I2 here. This is not good for the user, since you can see the ranking order between A2 to A5 does not change anymore, and the user needs to inspect all the 3 false alarms to discover all true alarms. The true alarms are below those false alarms. So, To address this issue, our solution is to perform counterexample-guided abstraction refinement. Here, the counterexample refers to those alarms whose probability drops are undesired. Take A2, for example. It is a true alarm, but its probability dropped after generalization. Hence, it is a counterexample. We find such a counterexample by sampling alarms whose rank drops the most. Here, rank drops of A2 to A5 are the same, and we sample two alarms, A2 and A3. Then we ask the user to inspect A2 and A3 and discovers that A2's probability first change and A3 correctly change. Now the target of our abstraction refinement is to remove information transmission from A1 to A2, but preserve such one from A1 to A3. This can be done by inlining read input even at 910 and separating a corresponding node tangent I to Y here. But another question comes: how to model such information transmission to guide our refinement? It needs a formalization to guide this refinement. Can we model just such transmission as a simple graph reachability problem? Okay, but our answer is no. Let's look at some Bayesian networks. Here, if A is read, then A is an apple with probability 0.5. If A is an apple, A is delicious with probability 0.9. Then given feedback that A is indeed delicious, the posterior probability of A being read will increase. However, if A is observed to be an apple, the feedback will not affect the posterior probability of A being read anymore. This is because such transmission is blocked by this observation. Another example is illustrated here. Here, otaku refers to those people being addicted to animes, idols, and all other possible things. Here, we offer two main courses, anime and idol, and I will show the type of my friend, Sky. Because please note that whether Sky is addicted to them are independent without any observation. However, now Sky is confirmed to be otaku indeed, but I know that he didn't love idol. Then we can easily infer that the probability of Sky loving anime will rise, which shows that given this observation, those two events are not independent anymore. Therefore, the transmission of posterior information is not a simple reachability problem, especially when we're considering observation. And the theory of conditional independence answers such problem. Here, the arrow from X to Y means that the information from X can reach Y. For more details of the theory, you can refer to our paper. Here, we just use this theory to construct the information transmission graph for our example program. And our problem reduced to cutting off A1 and A2 in this transmission graph while preserving such connection between A1 and A3. However, such problem to seek a min card to separate a pair of nodes and meanwhile ensures the connection between another pair of nodes has been started in a previous work, which shows that it is NP-hard. Therefore, we just reduce it to a partial weighted max set problem, and then we can solve it using a max set solver. The details of such reduction are also given in our paper. You can refer to that. Finally, with the information transmission graph, it is easy to say the cheapest way is to remove one edge on the path tangent I2 to tangent 1 and to alarm X2. It can be realized by inlining the corresponding node tangent I to Y. After such refinement, those true alarms and false alarms are divided. Then the ranking of A4 will shift to precede A5. Although the user needs to inspect A3 during sampling, the number of observed false alarms reduces from 3 to 2. Note that our refinement is the most efficient and proper to divide those alarms. For example, if we just inline read input even at 9, and encode it as node tangent I to 1, it is easy to say we cannot divide those alarms, and it is bad. Finally, we show the workflow of our framework, Bayesian Refine, which is an abstraction refinement module atop a previous Bayesian program analysis system, Bingo. It will first sample several alarms for the user to inspect, and then just use these inspections and leverage the conditional independence theory to construct an information transmission graph based on the derivation graph. Last, we can just refine the abstraction and change the structure of the derivation graph, then start a new iteration. In order to evaluate the efficiency of our approach, we conducted experiments on it. We used two instance analyses, a data risk analysis and a threat escape analysis. Our benchmark consists of 12 Java benchmarks from the decouple suite and from past works. Our baselines are running Bingo without refinement using abstractions produced by BingGraph, which is our previously proposed offline approach. Our major evaluation metrics are also offered here. We first researched how effective is Bayesian Refine. First, our results show that Bayesian Refine improves BingGraph's performance on both two metrics and two instance analysis. In summary, Bayesian Refine is indeed effective. We also evaluate how effective Bayesian Refine is under different training sets. Here, FTP GSpider and FTP HEDC use different corresponding programs in the benchmark for training. And we discover that when the training set selection is suboptimal, the improvement is even more significant as shown by those reduction. And from the perspective of machine learning, Bayesian Refine can be regarded as a structured learning approach, and we also compare it with a parameter learning approach, Bayes Smith. And the results show that while the reduction of parameter learning alone is less than structured learning alone, combining them produces the best results, which indicates that they are complementary. Last, we researched whether Bayesian Refine is efficient enough to scale. We discovered that a refinement module incurs little overhead here, as shown by refinement time, while the average Bayesian inference time also decreases. Moreover, we researched the data log-based analysis of the refinement, and we discovered that the abstraction is not refined too much. Finally, I will give the conclusion of our work. First, we propose an online abstraction search framework that is akin to CIGAR to solve the overgeneralization problem. Next, we propose a technique that identifies the abstraction to refine by leveraging the theory of conditional independence. Last, we evaluate our approach with two realistic analyses and demonstrate improvements to our existing offline technique. That's all. Thanks for your listening.
Questions? We have time for exactly one question by the next speaker.
Thanks for the talk. Do you use the results of the analysis to also perform some optimizations? For example, the results of the thread escape analysis, were you able to translate them to, let's say, remove locks or any other dependent optimization?
Excuse me, you mentioned a thread escape analysis.
Yes. So once you perform the analysis, you got improvement based on refinement.
It is a coarse analysis. We just model all heap objects as an abstract node, and it is just for testing. That if you want to refine that, you just drop that heap object from that coarsest abstract node and drop it and form a new node in the graph.
Okay, so it's basically analysis and not optimization, right? Yeah. Okay, that's all.